what we did was the following. So this is a nth supposing this is the nth order inhomogeneous differential equation. These are all functions of x coefficients. A naught x y equal to f of x. So that is nth order inhomogeneous differential equation. Okay, the right hand side f of x is not equal to 0, so it is inhomogeneous. So basically, this is an alternative method for calculating that's what we want to do, and get the solution y of x for this inhomogeneous differential equation. Okay, the L operator here is what? The L operator is nothing but this. Right? And if this is the L operator, then we know how to write this equation. L operator y of x is f of x. This is a concise notation for our inhomogeneous differential equation. All right. Now I'm also going to write this as this nth order differential equation. So I can write it like this. My L operator to be like this also. And going from 0 to n. N because nth order, n equal to 0 will give me that. Okay. All right. So what we did say last time was the solution of an inhomogeneous differential equation like this, and we are trying to solve this in a certain domain, a less than x less than or equal to b. That's the domain in which we are solving, and we will also be, subject to some boundary condition. Okay, I'm just going to say y a y b equal to 0. So we are trying to solve this inhomogeneous differential equation in this domain, subject to some boundary condition. Subject to boundary conditions. All right. So what we said was last time, y of x, the solution of such a inhomogeneous differential equation is given by integral of Green's function, which is a function of two variables. We use the same notation, generating function, don't get confused, but this is a different beast totally. Green's function, function of two variables, and the inhomogeneity term. Here it is f of z. Okay, so this is inhomogeneous term. All right. I can always write f of x as what? I can write f of x as right, where Dirac delta function exists only for x equal to z, and everywhere else it's 0. So, so this is your Dirac delta function. So L operate, if y is that, then I'm giving you a different way of maybe proving that we did write it, because that's the main thing which you're going to exploit today. So L operating on y, L operating on y of x is nothing but, L is nothing but all these differential, right? So I can do term by term, I can take the differentiation inside the integral. So we can, because they're linear operators, we can take it inside. So L operating on yx can be written as a integral of L operating on g f of z dz. And this is nothing but my inhomogeneous differential equation, which is f of x, right? And f of x is nothing but, I can always write it like that. So what I have is a to integral of L operating on the Green's function is this. So I can claim L operating on G is nothing but that. The L is the same, linear operator, differential operator of the original differential equation. Okay, so we are going to start with this, and we're going to exploit this particular, property for constructing the Green's function to calculate the solution of the inhomogeneous differential equation. Okay, so what does it tell you? So just let us try to understand this. L operating on g of x. So what do you know about Dirac delta function?
In terms of how it's behaved.
Yeah, I mean, so everything I'm going to talk about Green's function is actually going to be based on Dirac delta function property at this point. Okay, so whatever you know, I mean, just tell me, and then from there, one by one, I mean, I'm going to list the properties of the Green's function and its derivatives, and we are going to exploit that to construct the Green's function. Okay, so what do you know about so far about Dirac delta function, or whatever you have learned in quantum mechanics so far?
Boundary conditions.
No, it just what is the uniqueness of Dirac delta function?
Somehow there's some constant between two variables.
No, this is a sharply peaked function, right?
Yeah.
It exists at x equal to z, which is infinity. At everywhere else, it is 0. So that is Dirac delta function. Okay, so that is what we have to exploit. Okay, I mean, in some sense, Dirac delta function is something a function which exists only for x equal to the argument. If delta x equal to 0, it exists. Everywhere else, it will be 0. In this case, for x equal to 0, z, the Dirac delta function will be infinity. Basically, it is really infinity. Okay, I mean, and everywhere else, it will sharply decay to 0. That is the property of Dirac delta function. Okay, so that is something you know. So what can you, based on that, what can you say about L operating on the Green's function? It is 0 every, so you can say basically for x not equal to z, it is 0. Okay, I mean, I've drawn it like this, but this is a very sharply peaked, this width is really small. Okay, I mean, so what can we say about, how it behaves for x not equal to z and x equal to z? I mean, right, I mean, there is something. For x not equal to z, it is 0. Okay, so L operating on the Green's function is 0 for x not equal to z. So what does this tell you? What is L?
Just linear operator is differential operator, and therefore green functions should be some constant.
No, just what is we have done. I want to tie back to whatever we have been doing that so far. What is L? L is that bit, that operator,
Yeah.
right? So what does it say? L operating on y equal to 0 would mean what? It's a homogeneous differential.
Homogeneous.
So G satisfied, it's almost like as though it is a solution of the
Yeah.
homogeneous differential equation. Okay, so that's the first property, just to because we know L, that's what we have been solving thus far, so homogeneous differential equation. So it appears as though it's almost like a, as I said, when we are complementing particular solution, is the solution of your inhomogeneous differential equation, right? So it almost looks like, it looks like, it is part of the solution, you can see, of the, whatever ER thing. Okay, so G, L operating on G, so that is first prediction that we can give. We have to go through several properties. So if you've understood that, I'm going to get these things out of the way. So So that is the first thing that we can say. Okay, so that's one of the properties of Dirac delta function I have exploited. Now, what else do you know about Dirac delta function? Is there any property that you have learned in quantum mechanics of the Dirac delta function that we can exploit?
Would the fact that it's infinite at x equal to z be useful here?
We will be using that in a different way at some point, okay? I mean, we will come to that, okay? In a minute, we'll come to that. But there's another important property of Dirac delta function. What is the area of the Dirac delta function?
It's just one. It's one.
It's 1.
Yeah.
So we're going to use that, okay? And it exists only in the small regime. Okay, sharply repeat, okay? Let us say it is as a function of x, then it is z minus epsilon, z plus epsilon, and epsilon is, almost tending to 0. And this is, let us say, as a, we're varying x, and we're looking at it in a small regime around, this is really infinity. I mean, as you approach x equal to z, it is going to explode, okay? And we also know the area. It doesn't matter, even if minus infinity to plus infinity, or whatever you do, it doesn't matter. It is this, around x equal to z is what matters, okay? So we can say that integral of Dirac delta function in this regime is nothing but 1. Okay, that's another important property of Dirac delta function, okay? All right. So let me, I think I need this. That's my differential equation. Let me just get that. Maybe this is good enough. so let us see, what does that tell me? If L is this operator, right? So this is nothing but L operating on G. If I have to do this other property I want to exploit, I want to integrate both. I have this, right? L operating on G is derived of the function. That is the property that we derived. So I'm now going to say, let's look at, because I know the property here, can I say something about this? Okay, that's what I'm going to come. Okay, meaning. So integrating with respect to x, right? Okay, okay, this is 1. Now L operator is nothing but, this is, the n derivatives are there. And I'm integrating over a very small regime only. So what does this tell me? Okay, so let me keep it here so that we can start looking at it at least. This is nth order differential equation, so it goes that way. So m, and this is x, let me write down, because these coefficients are the function of x. All right. So I'm going to now expand my L, and integrate term by term. Okay, let us see what happens. M equal to n. Let's go with the highest term first. A and x, nth derivative of g with respect to x, x comma z, z minus epsilon. Okay, all this we are trying to calculate in the limit epsilon going to 0. Okay, all this is true in the limit epsilon tending to 0. It is, the width of that is really. Okay, so times dx, that is my first term there. I mean the last term there if you want. Plus, it'll be like that. We can now. I'll just write a few things and you from there will predict something. N minus 1, that's the derivative of g with respect to n. Of x of z dx, z minus epsilon, z plus epsilon. Okay, a0 x, perhaps. The last one there is that will be g of xz dx, z minus epsilon, z plus epsilon equal to right hand side is 1. Okay, that we have to keep it. Okay, I've done nothing but just expand so they understand what I have to say something with the derivative of g. That's what I'm going to be doing. So the first property we said was g has to satisfy the same for x not equal to z. It looks like it satisfies homogeneous differential equation. That's the first property. I'm going to now erase this so I can start writing other properties. So how can I satisfy this particular condition? I have to have this right hand side to be 1, and I got so many terms. So when you integrate this, because we are doing in a very small region, epsilon tending to 0, this is really a constant in that regime, right? So I can pull it out and I can write this term as a n z, and when you integrate this, what it is n minus 1th derivative of g with respect to x, evaluated between z minus epsilon and z plus epsilon, and so on and so forth. I'm going to write the next one and say something about the properties, and this will be this n minus 2th derivative of g with respect to x in this regime, and so on and so forth. And so what I'm going to say is the following.
Yeah, what's the property?
What is it?
I can't read the handwriting, but is that Is that L?
Which one? What is L?
Z plus L.
This one?
No, above
This
it.
is equal to 1.
No, above
Oh,
it. So, in front of the integral,
Limit.
Which one? Here? This one?
yeah, what does that say?
Limit.
Yeah.
Oh, okay.
Limit epsilon tending to 0. Okay, so I mean this is, we are integrating a very narrow regime, okay, that's all it is. This f inverse is really tending to 0, it becomes, shoots up to infinity, okay. Okay, so it's just, you know, at least you can understand this is going to be n minus 1th derivative. But I have to have this to be 1, right? So what it is the following. I'm going to write it and then I'm going to make you understand. Supposing, okay, so let me just see. I have to make one by one. The infinity that you said also, I want to make a remark on that. So what it tells me is, supposing I have this expression, term by time you can integrate, and supposing my all the derivatives, the n minus, if nth order differential equation, all the other derivatives, n minus 2th derivative, n minus 3th derivative, and including the Green's function, is continuous at x equal to z. Supposing we make that assumption, then what happens is these terms will become 0, because if it's continuous means it has the same value, you know, for upper and lower limit. So all those terms will be 0 except this particular term. So what you say is, for nth order differential equation, the n minus 1th derivative will have a discontinuity, and the discontinuity is of the order of, magnitude of the discontinuity is 1 over a n z. That's another thing we have to do. So let me just write down the statement and then make you understand. Basically state at this equation, you will understand it. So what we have is the following. For the nth order differential equation, n minus 1th derivative of g xz is discontinuous at x equal to z, and the magnitude of this discontinuity is simply 1 over a and z, and then all lower derivatives of g, including the Green's function, which is the, you know, no derivative. I mean, all lower derivatives of g of xz is continuous at x equal to z, including the Green's function itself. Okay. Let me just see if you are able to see everything here. Let me just erase some so that you can make it. It's easy to read. Okay, so all these derivatives, blah blah blah, is equal to 1, right? So what I'm trying to say is, only the first term at the upper and lower limit, it's discontinuous. So when you calculate it, it is not equal to 0. But here, if the second derivative of g and including the Green's function, if it's continuous, that means it has the same value for the upper limit and the lower limit, right? And it is so small, and so I can a and x can be pulled out and put it as a n minus 1z, okay? So that is equal to, and this one, the last term of course is a0, the Green's function, we had a0 what, x, right? I mean, we reverse that, but we are going to integrate that. between z minus epsilon, z epsilon, g of xz dx, right? This term, when you integrate, will become, if the Green's function is continuous, this is nothing but a naught z times Green's function, whatever it is, doesn't matter, it's a almost constant, it's a smooth function, it's almost constant, then all you have to do is, x, integral dx is x, which will be 0 for upper and the lower limit. So if the Green's function is continuous, this term is also going to become 0. Okay, so that's all you have to know. So all of them will become 0. Because that is what we are going to do to construct the Green's function. And Dirac delta function, this is not integration, so that is infinity, right? And what that tells you is nth derivative of the Green's function is infinity at x equal to z. So we have everything like the n minus 1th derivative has a discontinuity because we integrated. Nth derivative of g is at x equal to is infinity basically. Okay, so that is coming from that property, whereas the others are coming by the integration of the Dirac delta function around x equal to z. So what we have done is, just because of this particular expression, we are able to say so many things about the Green's function, the properties of Green's function. It is continuous. Green's function is continuous at x equal to z. Okay, that is the first thing that we will use definitely for a second order differential equation. And the first derivative of g will be discontinuous, and amount of the discontinuity is the following. Supposing I have a second order differential equation like this, something a2, we call it. Okay, I have supposing I have an equation like this. Let us say my first term, let's say that is 0. Like a simple harmonic oscillator kind of equation, right? Some inhomogeneity is here. Supposing that I have some equation, a1 is 0, but I have something like this. Then what it tells you is, if I had some equation like this, it will tell me the first derivative of g, that will be discontinuous, and the value of that is simply 1 over a to z. This is the important. Although the differential is independent variable is x, after the integration it becomes a and z. So the coefficient has to become a to z. Okay, that is an important thing. It will become very, very important in constructing the Green's function. So that is coming because after you take the derivative, it's a smooth function. You just take it out. But it's such a narrow regime. Its value is a and z. Okay, so that's what it is. So and you only integrate that part of it, and which is n minus 1th derivative. Okay, so that will be the thing, and then the Green's function itself, that is continuous. So what does mean? This is equal to 0. The upper limit and the lower limit is 0. So the continuous property and the discontinuity property for a second order differential equation, this is all you have to do. Okay, most of the time you're going to be solving second order inhomogeneous differential equation. Although I have done that generally for nth order differential equation, these are the two things we will be exploiting. The other property that we have to exploit is the following. This is about the Green's function itself.
Professor,
Yeah.
wouldn't it be like the second derivative or the first? This one?
What did you say?
The first derivative or the second derivative of x?
No, it is, as I said, if it's a second order differential equation, because, how did we get the condition on the derivative? We got it by integrating this. That's why I was showing that equation, right? We have to prove we got those conditions from here. Okay, if if the second derivative, then the leading term is d square g, whatever it is, your coefficient a2x. This has to be integrated, right, between z minus epsilon, this is within it, sorry. The leading term, if your equation was whatever, I mean a2, let's say original equation was something like this, even you have a1, doesn't matter at this point. Okay, all of them is function x plus a0 x, y f of x, something. Why is first derivative, right, you're asking? That's because L is this, right, the leading term is that, and I integrate that. So when you integrate that, that term becomes what? a2x d square g dx square. That is being integrated between z minus epsilon and z plus epsilon dx, right? So this such a small regime, I'm going to pull this out as a to z. So I'm approximating this integral, which is, this will be like a to z integral of d square g dx square dx, okay, which is the first derivative. So the discontinuity is on this first derivative, not, so that is nothing but dg over dx. That you have to evaluate. Okay. So that is the leading term, which has to be, should become, others you are going to make it continuous. So the next term is Green's function itself. You're going to say that is going to be continuous. If it is continuous in the upper limit, then its epsilon is limit epsilon going to 0 to the same value, so it just cancels out. Okay, so the Green's function is continuous in those cases, and this one, and that's why you get a to z. So the discontinuity is whatever is the coefficient, supposing it was x, okay, so you have to write the discontinuity to be 1 over z, okay, rather than 1 over x. So you'll get a total error if you just did not change the thing. So that is an important thing. Also, you have to change the coefficient, whatever it was. If it's x variable, you have to change that to a to z. Okay, that is yeah.
Sir, I have a question. A to z, which means when x equal to z, but the delta function means a to z when x equal to z, that will go into 0.
No, we are.
So the gradient of the Green function will be 1 over 0.
No, I don't understand what you're saying, okay? We are integrating this. This is what I'm saying. We are not just looking at this at all, right? We are integrating this equation. This is your thing. We are integrating this. Okay? That is 1. The right hand side is 1.
But I mean, your equation on the top, that's the gradient of the Green function.
No.
It's not integral.
No, that is right, but that's coming from here, this formula, right? What I'm trying to say is, we have this is not the only thing, okay? This plus, you got other terms here, right? L is not just this term, you got A1Z, you have other terms too, right? I mean, there are other terms, and all of them has to satisfy this condition equal to 1. So what we are trying to say is, other terms are 0, okay? They are continuous. This is the only term has to be discontinuous to become, to have that condition satisfied. Because right hand side is not 0. Right hand side was 0, then maybe every term we have to say. But the right hand side is 1 because of the integration of the Dirac delta function. And that gives you a condition on the leading derivative. If it's nth order, it's giving a condition on the n minus 1th derivative. All others we have made it continuous, so we made them others as 0. Okay, so it depends on what is discontinuous depends on the order of the differential equation. If it's a second order differential equation, it's the first derivative of Green's function, Green's function will be discontinuous. If it's a third order differential equation, then it will be a second derivative of Green's function, which will be discontinuous, and the rest of them will be continuous. So, they will be 0. It's coming from just the property of Dirac delta function. So that's all I'm trying to say, that this is coming there, and if you don't do the derivative, we can say for x not equal to z, it is 0. It's x equal to z, it is infinity, right? I mean, that is a property we are trying to exploit, the actual property of the Dirac delta function. So what, like if you have a step function, like that is discontinuous, right? So any function, and you take the derivative of that, that will be, Dirac delta function. I mean, so one, yeah.
So the n minus 1 is discontinuous. All terms lower than that go to 0. How do we get rid of the nth derivative?
Nth derivative, no, that is coming, nth derivative is infinity. That you're not getting rid of it. That's what I'm trying to say. Nth derivative of g is infinity.
Right.
Because there we are not, I mean, we are not, we are just, all we know is this formula, right?
Well, I see in this case the nth derivative is 2.
And nth derivative of g is, because x equal to z, we are not integrating, so Dirac delta function at x equal to z is infinity. So nth derivative is infinity. Okay, so we are just analyzing not only Green's function, first derivative, second derivative, every derivative, how it should behave. We have a property based on this one expression, okay, which we got. Okay. And L has, whatever it is. I mean, it depends on the order of the differential equation. But for our purposes, we are going to be doing second order differential equation only. So all we have to find out is, Green's function is continuous, first derivative is discontinuous. And the amount of discontinuity, for instance, I mean, if it's a like step function, let us say, what is this, discontinuity? That discontinuity, the height of it will depend on, whatever the coefficient is here of the term, okay? And that's all it is, yeah. Okay, so that's, so these are the properties, and one more thing I have to add. So this is a problem we are solving subject to some boundary conditions, okay? So another property that we will be using in getting the Green's function is that Green's function, as a function of, if z, as a function of x equal to a, right? I mean, and any z, it will satisfy the same boundary condition as g at x equal to 0 in this case, and any z will satisfy the same boundary condition as y at, in this case, x equal to a, okay, and similarly this. Okay, so they will satisfy the same boundary condition as y, whatever it is. Okay, so, and that sort of is easy to understand from the previous method actually, because if you remember the way we wrote the solution as linear combination of eigenfunctions, and my Green's function was given as y and x, y star, complex conjugate, and z, right? Eigenvalue, and going from 0 to infinity. So, so if y is expanded in terms of eigenfunction is Green's function in terms of that, so it has to satisfy for x equal to a, same boundary condition as y, and at x equal to b, the same boundary condition as, y equal to b. That's the reason why we have this boundary condition. So we have to exploit all these properties also. Okay. I'm going to combine into one. Green's function will satisfy same boundary condition as y. Okay, so maybe as a function of x alone I will write, because it's a function of two variables, right? As a function of x alone will satisfy the same boundary condition. So okay, so those are the first thing to remember is Green's function looks like as though it satisfies a homogeneous differential equation. So we will sort of use that to first guess the functional form of Green's function as a function of x and z. Okay, so that will be the first step, and it will have some constants and all that. On all those things we can evaluate only by using the boundary condition and how the continuity and discontinuity property of the Green's function. So it starts from this. This will be the first one for x not equal to z. I mean, that's important. Okay? I mean, x equal to z, it becomes infinity. So that is another thing we will have to, how to consider Green's function. We'll come to that. So we'll start with that, and then exploit all these properties, including this, that g at x equal to 0, any z in this case is 0, and g at x equal to x equal to a, sorry. X equal to a, x equal to b, at the boundary condition is 0. Okay, so those are the properties we have to do. 1, 2, and the important thing is Green's function is continuous, that's important.
Under yn.
Okay, that is continuous, and this one is discontinuous of this order, that one we have to use, and this one we have to use. Okay. Clear? Yeah.
Is that supposed to say Green's function will satisfy the same boundary condition as y sub x, or it's supposed to say Green's function?
As a function of x alone, because I'm saying this because g is a function of two variables, x and z, right?
Mm-hmm.
So y is a function of x only. So for when x equal to a, it will have the same boundary condition. For any z but x equal to a.
Okay,
Any
so-
z but
so-
x equal to b, it has to satisfy that
So
boundary
the
condition.
full sentence should say Green's function will satisfy the same boundary condition as a function of x alone.
As a function of yx, as a function of x, yeah,
Okay, sure.
yeah. But any z, yeah.
But any z?
Right, because they're not changing, because I mean, y is a function of x only, right? So I can only talk about that. You can see, look at this expression, right? I mean, when we know what is x equal to a, what happens. So I'm going to put x equal to a, what happens, whatever the boundary condition is, it should satisfy that. I mean, just following from these expressions, that last condition is coming from that. So this condition, we can call it as boundary conditions on G. Okay. Boundary condition, continuity property of Green's function, discontinuity property of the derivatives of the Green's function, and the fact that it satisfies homogeneous differential equation. So those are the 4 properties which are important, that will be used. To discontinuity is the 3rd property, and continuity property you can want to call it 4, and you can call this as 5. All right? Is it clear? This concept you have to understand because before we start doing a specific problem.
You're saying those are the steps?
Huh?
Are those the steps?
Right, yeah. So, is it clear? I mean, I can rewrite it if you want. The first step is it satisfies a homogeneous differential equation, okay? LG of xz is 0. That's homogeneous differential equation. So we will predict the functional form of Green's function using solving the homogeneous differential equation. Then we'll say if it's a second order differential equation, we'll say the first derivative of Green's function is discontinuous, and the amount of discontinuity is equal to the coefficient of the second derivative, inverse of the coefficient of the second derivative at x equal to z. And the third condition we are going to use is the Green's function is continuous at x equal to z. At the point of discontinuity, it is, the Green's function itself is continuous. That is basically L of g, right? Okay. So it has got all the derivatives. And we're going to say Green's function satisfies the same boundary condition as y of x, for which you're trying to, the solving the inhomogeneous equation, differential equation subject to the boundary condition, right? So those are the 5 conditions. So let's do a problem, maybe it will become clearer. So it's got some concepts, that's all. Everything is based on the Dirac delta function, property of Dirac delta function. That's it. Integral of Dirac delta function, is 1, but Dirac delta function by itself, you look at it at x equal to z, it will blow up. At everywhere else, it's going to be 0. Okay, that's a property we are trying to exploit. Okay. So what is the L operator here? All right. And we are solving this subject to the boundary condition y at x equal to 0 is 0 and y at x equal to pi over 2 is 0. All right. So if this is given, you automatically know the regime in which you are trying to solve is 0 less than x less than pi over 2. Okay, so that is your lower and upper limit. Okay, what is the L operator? First we have to identify your L operator. Yeah. This plus 1, right? So this is your Ly equal to f of x kind of a thing, where f of x is cosine of x, cosecant x, sorry. Your inhomogeneity is cosecant x. All right. Given that, first what did we say? We're going to set up the homogeneous L of g. This is the differential equation. We have to do L operating on g x of z equal to 0. L is the same operator as what was your differential equation. So we have to solve this equation, d squared g over dx squared. G is a function of xz, okay, plus g of xz is 0. So that is this equation, basically written in, expanded the form because L is that. Okay, what is the solution of this? This is our simplest differential equation we have come across, right? Except what is the difference? We have, in a simple harmonic oscillator we have come across, right? D square y over dx square plus omega square y equal to 0. So what is the solution of this? This is the one where we can guess. Forget about z, okay? Supposing you had some function d square y over dx square plus y of x equal to 0, what is the solution? We start started our course with this, right?
E to the
Maybe omega squared y or something. What's the solution of y of x in this case? This is equal to minus omega squared y, right? That's your simple harmonic oscillator.
To the
e to
power.
the plus minus I.
Or you can write it in terms of sine and cosine, right? This is how you would write. You can just substitute this 2 times, take the derivative, and you'll see it will satisfy that. Except I have now, it looks like that equation, right? It's exactly like that, except omega squared I put it as 1, and then omega squared. So here it's a function 1 variable. Now I have g as a function of 2 variables, x and z. So what modification should I do? Otherwise, the differential equation looks like whatever we have come across. But I need
Like
to,
the plane wave.
The relation can be anything. Okay. Between x and x.
what is the simplest extension of this equation to get a solution?
Sin
Just,
x plus z.
hmm?
That's cos.
This is clear, right? I mean, yeah, okay. Very simple extension. You don't have to think very complicated.
It's cos x plus z.
Can I just make the function not constant? I mean, so we don't know what it is, we have to figure it out, okay? I mean, so I'm just going to make this as a function, okay? So I'm going to write this as sine of x plus bz cosine of x, right? Because omega squared here is 1, okay, for me. It's just a simple, and we have to find the functional form of a and b. I don't know what it is, we have to find it. That's what, all those things will come from all the boundary conditions and all the properties that we have. Okay, so that is, so we are solving the homogeneous, this is your homogeneous differential equation almost. So this is true for x not equal to z, right? I mean, it's not, x equal to z is not the case. So this is a homogeneous differential equation kind of a thing. All right. There is one more complication that I'm going to bring up at this point. So I have put all the z dependence on these coefficients basically, right? And what I'm going to say is, because I do know, if L operating on G is, blowing up, and there's a discontinuity of the first derivative of the Green's function. That I know. How do I then, get it? So what we are going to do is, I'm going to have a different superposition of the Green's function for, below the discontinuity and above the discontinuity. Okay, so x, I'm going to say it has a different superposition for x greater than z plus epsilon, where epsilon is something going to 0. Okay. So that will hopefully bring up the discontinuity of G, whatever is the discontinuity, and but G itself, I'll force it to be continuous at x equal to z. But this is to get the discontinuity of the first derivative. So that is so basically, if it is something is discontinuous, I have a different superposition for x. This is, let's say, where discontinuity is, and this is slightly above. So x equal to z plus epsilon and this is x equal to z minus epsilon. So it will be different superposition of the function that is going to describe a step or any when you have a jump or discontinuity of a function. So that is what we have to mimic. So this is the first step. Okay. So we have different functional forms. We are going to say for x less above and below the discontinuity point of the discontinuity point. All right. Now. All right, what else? Can we start maybe apply the boundary condition first? I mean, g at, g at x equal to 0 and any z is 0, right? This is above the discontinuity, right? So this one, this boundary condition I'm going to apply to the first equation, okay? The other one is at the other end of the thing, right, in the domain. So I'm going to use g pi over 2 comma z equal to 0. I'm going to apply to this second form of the boundary condition because that is the functional form I'm proposing for above the discontinuity point. Okay, wherever the Dirac delta function was, or so the whatever the function is, it will have, one derivative less than that will have some discontinuity like that. The function is like that, then it will have, it's going to, in the first derivative will have, of that function will have discontinuity, it will explode at x equal to z. All right, so if you understand that, let's just, that will simplify what form, what coefficients will survive. So g of x of z, x equal to 0, this is 0, so implies b of z should be 0. Okay, so that means this condition tells you b of z is 0, and this condition we have to apply to this one. X equal to pi over 2, this is survive. That is, but it has to be 0. So that tells you c of z is 0, right? So g of xz is then has this form a of z sine x for x less than z minus epsilon. So we normally also represent this with this, just remember that it is below the discontinuity point and is equal to d of z, is that correct? Cosine of x for x greater than z plus epsilon. This is for, let's say, g, just to remember, this is that regime. Okay, that symbol is normally used. Pi over 2, this is 1, and that is 0. And the only way it does it will go to 0, so that's okay. I'm just trying to say I have the correct functional form. So in one regime you have sine x, the other regime you have cosine of x form, and I still have to calculate all these things. Okay. All right.
So the G with the
Greater than sign.
that's for the right hand side of
That
the
is that means this, yeah, this regime. Okay. Yeah.
the region to the right side of
Right,
the
right,
curve.
right side of the discontinuity. Yeah.
Okay.
Yeah, wherever the yeah. It's exploding. Yeah. This is just to remember. That's all. You don't have to. If you put it there, that's fine. If you forgotten to put that, at least that will tell you. Which regime. This will become very important a little bit later when we try to calculate the solution. Now, what else can we? So we have got the Green's function, some functional form we have got. What are the other things we can apply?
N minus 1.
We can first we have to say Green's function is continuous, right? And then first derivative is discontinuous. Okay. Luckily in this case, a2 is 1. All right. So 1 over, I don't have to worry about it. It is 1. Okay. So So in this case, it's a little bit simpler for us. Okay, now before, this is another thing, why I'm saying this discontinuity property, we have to do it carefully is, remember we did z minus epsilon, z plus epsilon, this should be 0, right? G prime of xz, z minus z plus epsilon equal to 0. These are the two conditions that we have to apply. Okay. Now, G, so this is the upper, this is the first thing that I have to do, right? The first condition is then dz cosine z minus az sine z equal to 0. This will lead to that one. But I have to take the derivative before we do that. But anyway, this condition will lead to dz. Because I have to choose that regime first. Okay, dz cosine of z minus az x equal to z, epsilon becoming 0, right? And so we have to put that also. Az sine z equal to 0. Is this clear? Value of g at the upper limit, which is the second one. This is the value of g at the lower limit, is this one. Okay, so we have to pick these things correctly, otherwise we'll get the incorrect thing. And then g prime, then I have to again, if we have to do first, in that regime. So I have to, g prime is, this is what g prime in this regime. Let me just write down here. G prime here in this regime is, I'm doing the derivative with respect to x. Okay, so dz sine z, cosine theta is minus theta. This is the derivative. And g prime is az cosine of x. Okay. That's the first derivative. So that at the upper limit will be then minus dz sine z x. And now I put z x equal to upper limit with epsilon tending to 0, and then minus, where is that gone? Okay, minus a of z cosine of z equal to, what is the right hand side? Is equal to 1. Okay, so because the first derivative has to be 1 over that, so this quantity is 1, this first derivative. So, alright, did I get the signs correctly? This is the upper limit, so this one minus dz sine z, because otherwise you'll get the coefficient incorrectly. Okay, alright. I can remove that because we don't need this. Okay, so you got two algebraic equation, and you can solve for az and dz. So we will have the full functional form of the Green's function. Okay, so let us get that. All right. So what you have is dz of cosine of z minus a of z sine of z is 0, and the other one is negative dz sine z minus a of z cosine of z equal to 1. All right, maybe we can multiply
Cos by
cosine here, right? And that will get, and then
No, first
the
equation by sine. and-
sine, the second by cosine, right? Okay, we can get that. So let's multiply. Don't forget the other side also, because I just want to put that. Okay, let me multiply this by cosine z. Okay, and let me multiply this by
Sine.
sine z. Supposing I multiply that, then I can eliminate dz, right? So I just add that. So I will have minus az sine square z, and I'm just adding them up, minus a z cosine square z equal to cosine of z, right? I don't forget, after do it in 2 steps, so you don't, because this side is not 0, right? So I have a cosine z there. Here I don't have. So minus az sine square z is fine. This is fine. I'm adding up and that, okay? All right, so once I have that, it's easy. Minus az sine square z plus cosine square z is cosine of z. So I have a negative az is cosine of z, or az is negative cosine z. So I have now the functional form of this, which is nothing but negative cosine z, okay? So I can come back, I can substitute here. I know this. So it has become minus cosine of z sine of x. So once you have az, I can calculate dz because it's a very simple equation. So d of z is nothing but az sine of z divided by cosine of z, right? And az was this, so it's nothing but negative sine of z. Okay, it's very symmetric. So this one, d of z is now negative sine of z cosine of x. All right. All right. So we got the Green's function. The whole thing was to construct the Green's function, right? Now there's one more complication at this point. Let's right. So our goal is to calculate y of x, right? Which is the regime in which a to b is 0 to pi over 2, because that's a regime in which we are trying to calculate g of xz, f of z, dz. Okay, so this is what we have to calculate, and what we have done is the Green's function we got. Now one more step, which is where most students make mistake, is now we have got Green's function for different superposition for different regimes. So I have to break this up. This limit, I'm going to say my variable here is z, not x now. Okay, so I'm going to say the discontinuity is in this case z at x minus epsilon. Okay, so I'm going to write it into two terms and pick the correct form of the superposition of the Green's function. And here I'm going to say x plus epsilon to pi over 2. Okay, and g of xz, f of z, dz. This is the integral that I have to evaluate. Okay.
Epsilon tends to 0.
Yeah. All this, I mean, it is.
Yeah, because otherwise then we need to consider one more interval.
No, it's always, I mean, when I say epsilon, it's limit epsilon tending to 0. Okay, now, what is the complication here? Here, I have to pick the correct Green's function, okay?
Yeah.
Here, what is it? Z is greater than x, right? I mean, z is less than x minus epsilon, right? I mean, or less than x, let us say, always, right? I mean, because it's going from 0 to this. This is the upper limit. And here, z is greater than x, right? X, okay. So the functional form for z less than x is which one?
Less than x.
Yeah, here x is greater than z, right? So
Yes.
it is the second one which has to come in the first. So you have to pick up the correct functional form because the variable has changed, okay? The variable here is z. So I need to pick up this. So g of xz, because z is now going from 0 to x, it is less than x. So I have to pick up this functional form. Okay, otherwise you're going to get incorrect results. Because there are two variables z and x, and you'll be integrating over the incorrect one. So that is typically a place you have to be careful. So y of x is nothing but 0 to x. I'm going to now write x, okay, not x minus epsilon. I'm going to pick up this one now, minus sine of z cosine of x. Okay, that is the correct Green's function for that. And then the other location we have to be careful is this f of z. Okay, so convert that into cosine z. Don't put it a cosine in homogeneity. So make that also now go to cosine of z dz. Okay, just don't blindly use the inhomogeneity because the variable is z now. Okay. Okay, so be careful there and be careful about, look at the independent variable and see which one we have to pick up the functional form. Plus x to pi over 2, and now I'm going to pick up the other one, which is minus cosine of z sine of x. F of z is now cosecant z dz. Okay, they are very simple integrals. Okay, I think we have everything correct. So what you have is then y of x. Okay, variable is z, so I can pull cosine of x outside. So I have minus cosine of x, 0 to x. This is what? Sine z cosine z, so that is nothing but dz. So that's a simple integral. And then here what do we have? Again, I can pull minus sine of x outside, x to pi over 2 of, we have what? Cosine of z over sine of z dz. Okay, so that is nothing but natural log of sine z, right? Numerator is the derivative of that, so this is nothing but natural log of sine z. Okay, natural log of upper limits not contributing. Sine is 1, log of 1, natural log of 1 is 0. So you have contribution from the lower limit only. So this will become what? Plus x what happened? Plus sine x. Is that what sine x? Negative, the negative will go away. So natural log of sine of x. That's correct. And this one is nothing but minus x cosine of x. Okay, is this clear? Is it all the steps are clear? So I'll repeat. Okay, I mean the first thing is write the homogeneous differential equation for the Green's function. You know, once you know the differential, you can write that, and then and get the functional form. Guess the functional form of the Green's function. Okay, for something like this, it's easier to guess, and you put, because it's a function of two variables, put the z dependence on the, usually we write as constant, right? And now we make it as variable. That's the only difference. And we want to just first guess for two different regime. At the point below the discontinuity and above the discontinuity, you want to get different superposition of the Green's function. And then we apply the boundary condition on g of xz for x equal to a and b, because it satisfies the same as y. And then we eliminate so that we can, you know, guess, get rid of some of them, a or b or whatever, a or c, one of them. That is what you do. And then we applied to calculate the actual value A and other constant, what we did was apply the continuity property of the Green's function, and the first derivative of the Green's function has to be discontinuous by that leading coefficient 1 over A to Z. So you do that and get then from there you get the value of A and another coefficient, let's say in this case A and D perhaps you got. And then once you have the functional form, the full functional form of G of xz, we have the Green's function for the entire regime. Okay, I mean, so all we have to is go back to our, the solution of the inhomogeneous differential equation, right? I mean, whatever it was. Go back here, and we split this into two regimes, one below the discontinuity and one above the discontinuity, and pick the correct functional form of the Green's function. That is important because otherwise you're going to get incorrect answer, because one has got cosine, one is sine, and so you have to do all that. So that is one, and then try to remember to change this to f of z. Don't put as cosine x, because again you'll get incorrect, because the two variables are coming, you'll get a completely different you may just factorize it out without integrating. If it is inside, you're going to integrate over that variable z. So those are the locations you have to be careful. Okay, otherwise you'll get incorrect answer. All right. So I have given a homework problem. Try to do that with both methods, one by eigenfunction method and by this. Don't try to compare the results. I'll tell you why. One of them will be in series form, the other one will be in the functional form, unless you know how to convert the series into functional form. So don't even worry, they don't look alike. That's because one method is going to give you, remember y and x, y, it's going to be in the series form. So don't, but they're equivalent, methods. Maybe in simple cases we can show they're exactly the same. So whatever appeals to you, you can always use either one of the methods. I mean, it is both are fairly straightforward. That's it. Okay, now main question, $1 million question. Are we going to have the test on Tuesday or Thursday?
Thursday.
Thursday? That's the.
But I want to ask one thing. If Tuesday the material, the next Tuesday material won't come in,
No.
then it's okay. Then I'm fine with it.
So it's always going to be the case, right? The reason why I'm putting, yeah.
No, I'm fine with both.
No, I just say, I mean, it is, I want you, because this is one of the main things I want, new material that I want you to be comfortable with, right? And I want you to learn it properly.
Thank you.